Today we'll be looking at calculating the apparent and active powers in a circuit. Now, this is a quick reminder, quick refresher. The apparent power of a circuit is a measure of the product of the RMS voltage and RMS current that is being supplied to the circuit. The apparent power is measured in volt amperes, while the active power, sometimes referred to as the true power, is the actual power consumed by the circuit, and this power is measured in watts. Now, the relationship, or the mathematical relationship, between the active power and the apparent power is that P is equal to S cos phi. And cos phi is known as the power factor. So P is equal to S times cos phi, where cos phi is your power factor. Phi, in previous lessons, is the phase angle. That's the angle between our voltage and our current, supply voltage and current. Now, there's another kind of power that is within an AC circuit, and it is known as the reactive power. Now, we won't be focusing a lot on this today, but the reactive power exists. And active power is consumed by the resistive part of the circuit. So that real power is consumed by the resistive part of the circuit, while the reactive power is consumed by the reactive elements. And that's really a misnomer, because we consider reactive power to be useless power because there's a transfer on each cycle of the AC. But that's not for today's lesson. But we just need to note that for the reactive elements, the reactive power is consumed. And the relationship between the apparent power S, the active power P, and the reactive power Q is that S is equal to S squared is equal to P squared plus Q squared. Now, let's consider this circuit. And the question here is that we want to determine the active and apparent powers and also the power factor of the circuit. So we want the active, we want the apparent, and we want the power factor. Now, in these questions, we always assume, unless we are otherwise told, we always assume that the voltage given is the RMS voltage. So there's no point in applying the 0.707 in this case. That's the assumption, unless you're told specifically that it is the peak voltage that you're being given. So how do we go about that? So for our circuit, we know that to find the apparent power, it is the voltage times the current. The current, of course, is equal to the voltage, the supply voltage divided by the impedance, and the impedance is equal to the square root of the resistance squared plus the reactance squared, where X is equal to XL minus XC. So for this circuit, we have an inductor of 38.2 millihenries and a capacitor of 530.5 microfarads, and the frequency is 50 hertz. So we want to find XL and XC. So XL, which is equal to 2 pi F times L, we have 2 pi times 50 times 38.2 times 10 to the minus 3. Let's calculate that. So that's 2 times pi times 50 times 38.2, and that gives us 12 ohms. XC is 1 over 2 pi times FC, and that's equal to 1 over 2 pi times 50, or frequency, times 530.5 times 10 to the minus 6. And that gives us that gives us 6 ohms. So the impedance of our circuit, Z, is equal to the square root of 8 squared plus 12 minus 6 all squared, and that is 10 ohms. So we have the magnitude of our impedance. We can use this to determine our current. So for our current, I is equal to supply voltage divided by our impedance, which is 30 over 10, which is 3 amperes. Our phase angle phi is equal to the inverse tan of XL minus XC over R, inverse tan of 6 over 8, which is equal to 36.86 degrees. So the full answer is that I is equal to 3 amperes at 36.86 degrees. And this is, of course, lagging. And it's lagging because XL is greater than XC. So we have the RMS value of our current. We have the RMS value of our voltage, which is 30. So we can now determine our apparent power. So S is equal to voltage times current. And that gives us 30 times 3, which is 90 volt amperes. Now, we were also asked to find the active power and the power factor. Now, our phase angle phi is equal to 36.86 degrees, which implies that our power factor which is equal to the cosine of phi, would be the cosine of 36.86, and that's equal to 0.8, which implies therefore that our active power P will be equal to S cos phi, which is therefore 90 times 0.8 to give us 72 watts. So for our circuit, we supply it with 90 volt amperes at a power factor of 0.8. Therefore, the circuit consumes active power 72 watts. But as we said before, the active power is consumed in the resistive part of our circuit and the reactive power in the reactive part of our circuit. So let us test that. our current, the magnitude of our current was equal to 3 amperes. Which means, therefore, that our active power from the resistive part, if it's consumed by the resistive part, P would be equal to I squared times R, which would be 3 squared times 8 to give us 72 watts. For the reactive part of our circuit, now Q would be equal to I squared X. And X here would be the resultant reactance. So it would be 3 squared times 6 to give us 9 6s, 54. And the unit for reactive power is vars. But we also know that S squared is equal to P squared plus Q squared, which implies that S is equal to the square root of 72 squared plus 54 squared. And that gives us, so that is 72 squared plus 54 squared. If we find the square root of that, we get 90. So this proves what we said with respect to how power is consumed in the circuit. We thank you very much for your attention, and we trust that this has made the calculation of power a lot clearer. Thank you.